So the goal for today, I'm going to show you a live demo about ImageJ, using ImageJ for chromogenic image analysis, from specifically single-plex chromogenic images. And as you can see in this outline, first, I'm going to give you a brief introduction about RNAscope, overview about that, and then what are the current methodologies that we use to evaluate or quantify the dots in these images. And then we're going to start with the ImageJ demo. Here's some disclaimers. I would like to emphasize that this demo is for single-plex chromogenic assays. If you're interested in fluorescence assays, we're currently working on that, and we'll give you an update about it in the near future. So let's get started with the first part, which is an overview about our assay. It's a quick refresher for people who already know that. So RNAscope works with a variety of samples shown here in purple and yellow. The most common of these tissue is formalin fixed paraffin embedded, known as FFP tissue. The tissue is placed in a glass where cells are permeabilized, and the target RNA is unmasked. This technique works on different kinds of RNA, such as messenger RNA and long non-coding RNA. After this step, after the permeabilization step, comes the hybridization step, which includes the hybridization of a pool of about 20 target-specific double Z probes, shown in yellow and purple here. These double Z probes target the RNA and allow for amplification of the hybridization segment, as shown in the next step, which is the amplification, which happens via sequential hybridization of amplifiers and label probes, resulting in detection of single RNA molecules as dots within a morphological context. And this is shown here. These dots can be viewed under a light microscope or a fluorescence microscope, depending on the label probe used. And they can be quantified on a cell-by-cell basis, which is covered shortly. More specific details about our assay is that it begins with a unique probe design for the detection of RNA. Probes are Z-shaped oligonucleotides, shown here, and composed of 18 base sequence, as you can see in the lower region, and these are connected to a 14 base tail sequence via spacer. When the pair of double Z probe hybridize next to each other at the target binding site, as you can see in this figure here, this form about like 50 base pairs along the target RNA. The upper region of the 2Z molecules now form about 28 base pre-amplifier region. This is important for signal amplification to occur. For each target RNA, a pool of about 20 double Z target probe pairs spanning about 1,000 bases along the target molecule are designed to specifically hybridize to the target molecule. Now, once the pre-amplifier binds to the target RNA, signal amplification can take place using an L-shaped pre-amplifier molecule, as you can see here. And this L-shaped pre-amplifier binds to the amplifier side, and the amplifier then binds to multiple sides, as you can see here. And finally, the label molecules, such as chromogenic or fluorescence, bind to the numerous sides on the amplifier side, shown in blue color here. Now, if one of the probe bind to an unspecific target, it's highly unlikely for another Z probe to bind, hence pre-amplification or sequence won't form. This what gives the advantage for our assay is that it's very highly specific and the signal amplification is very robust with background noise suppressed. So this is just an overview about this assay. Moving on to how do we quantify these dots. So we typically follow 3 methodologies to do the quantification. So the first one is semi-quantitative, as you can see here. The number, and within this methodology depends on the manual users or manual scoring scheme, where the number of dots per cell is measured or estimated. And based on this ATD table, where it shows you a score for every range of the estimated dots per cell or measured dots per cell, you can have a score for the whole image. We call this semi-quantitative way because it depends on the pathologist or user who's scoring these images. Now, this table can be condensed or expanded depending on your application, as long as you have a reference point for all your slides. For comparison, you can change the range the way you want. The next step, or the next methodology that we use, is the image-based quantitative software analysis. So you need a software for detection of the dots, also detection of all the cells within your slide, and you need the software to be able to report back these numbers to you. And at this point, you have the freedom to report the result as average dots per cell or average dots, their ROI, or the total number of ROI. So the key here, as I mentioned, is to have a software that can do this process for you. And ImageJ falls into this category, and I'm going to show you how you can count these dots within your field of view or within your image, and how we can count the cells and report histograms or averages such as the ones shown in this diagram. The third method is more about showing the dynamic range of expression. So, and to do that, you should be able to, within your image or whole slide image or field of view, you should be able, whether using a software or semi-quantitative method, to find out the percentage of cells within each category. So as you can see on the right, there are different bins, and each bin shows a different range of expression. And depending on your percentage of cells and the number of dots within a specific region, you can bin them into these bins or different categories within these bins to calculate what we call a HISTA score or H score, or you can even draw them in a histogram, and this will be the profile of expression within your slide, as you can see in the right-hand table and histogram. I mean, the advantage of this method, as you can see, it shows you the dynamic range, what percentage of cells you have within each category, and squeeze it into just one score or even a profile, so we can have better comparison between your samples and slides. Now, after this overview, let's start with ImageJ, and I'm going to show you how we can do the segmentation of cells and dots, and how we count them. So ImageJ, the version or the distribution that we're going to use of ImageJ is the Fiji distribution. The download link is as shown here. And as I mentioned, we're going to go over different detections within the image. So we're going to use this image. It's a stomach tissue that we're going to use, and the signal or the probe that we are trying to detect here is a brown RNAscope based copies for this probe. And then so the goal here, we're going to count the cells. So I'm going to show you how we can move from image like this to this, and the modules that we're going to use. So let's get started with this. So I opened the image, as you can see here, using PG version of ImageJ. So the first step, you want to zoom in to a region in your image where you can see all three colors. So the three colors here that I'm interested in is the hematoxylin, the brown signal of the probe, and the background. You need three colors to deconvolve in order to get the nuclear color or the nuclear image. So let's do the zooming. So I clicked here on the magnifying glass. I'm going to zoom the region here. So it's very important in order for image deconvolution to work, that you choose pure colors for the three colors that you want to deconvolve, which means you don't want to select a pixel that has a mixed signal between the three colors. So, for example, let's see. So here, this region might be a good candidate for hematoxylin color, but not this region, since it has mixed colors. So let's get started. So we're going to go into image, color, and color deconvolution. Shown here. Now, if you look at the module itself, it gives you presets that can be used, so you don't really need to define the colors. Today I'm going to show you the more general approach, which is from ROI. However, that doesn't mean these won't work. And they depend actually on the quality of the image. So sometimes if you choose H&E, it should work in these images. And remember, we're only interested in the hematoxylin in these images, not interested in other colors. So even if you choose the hematoxylin, one of the colors should be one of the results should be almost the correct hematoxylin. However, sometimes this won't work because, as I mentioned, these are presets. So that's why I'm going to show you the more general approach and how you actually get the image of the color that you want exactly. So if I click on From ROI, and then I click OK, it will ask me to select the first color. So let's select, that's OK. And let's select, let's say, this is my hematoxylin color. And left click to confirm the selection. Now let's select another image or another color. Second color will be the brown color that I want to deconvolve. So let's hit OK. And let me select this last one here. And the third color will be, as I mentioned, is the background color. So let's select it to be here, which is this light color. And now, after you do this, it will give you the results of three images, three colors that we deconvolve, as you can see here. We're only interested in the first image, which is the hematoxylin image. Now, as you can see, we have here, we don't have the other probe signal. It's just pure hematoxylin. Now, make sure when you do this step and inspect the quality of the images afterward, that you don't have many holes within the nucleus, because this will affect the next steps for segmenting these or separating these nuclei from each other. So after you finish, I like to save the results of each step. So let's say you want to save this image and you're satisfied with the results. You're going to save it as this, for example, in step 1. And it says color 1 here. And this is ready, let's say, after you are satisfied with the quality of the deconvolution, you can carry this on to the next step. Let me show you why it's important to choose colors carefully for the deconvolution. Let's say, let me close out this and let me do this step again. Let me zoom out first, which is another reason. Now, if you don't choose pure colors, this will result in low quality deconvolution. So let's say for some reason, let me open it. You select the first color, which is almost pure hematoxylin. You need to select the second color, which, let's say you select this color. Now, this selection is wrong because in that particular pixel, there is a mix between hematoxylin and the probe itself. So this will affect the deconvolution itself. So let's see what happened. Let me say I selected this to be my second color, and this here to be my third color. And let's look at the results. Still, the deconvolution gonna work, but now if you look at closely at these nuclei, you can see you get more noise, you get more holes than the nuclei, and we get all this artifacts due to this selection. So at the end, like, it's an optimization process. You want to go back and forth. If you're not satisfied with the deconvolution itself, you can go back and do the selection again and try to separate the colors by eye as much as possible, the selection as much as possible from each other, and try to avoid choosing pixels that are possibly mixed color between these three components for the image. Okay, so let's move on to the next step, is how we're going to count the nuclei in this example. Let me open my image, the one I just saved. I have another one too. Let's open this. And now we're going to do thresholding on this image. So we're going to go to Edit, or sorry, Image, Adjust, Threshold. And make sure the nuclei are in a black color here for the next steps to work. So I just deselected that color if it's selected for you. Now here you can use different algorithms, automated algorithms, to do the thresholding for you. also is a very good one to separate two populations from each other. In our case, is background and discard. And then you hit apply. And now we have our thresholded image. Now, if you look closely, you can see still we got noise in this image within the nuclei. So there are different methods to clean up this noise. One of the methods that we use, if you go to process, if you go to binary, and you do like closing operation, you can see now we got rid of these small noise pixels within these nuclei. So you're going to go to process again and do binary and do open. It's also get rid of some of the noise within your image. Now, for me, like this still like not optimal segmentation, so I would go back and optimize this again for the color deconvolution to get rid of more noise here. So maybe my selection weren't optimal. So it's an iterative process. I would go back and maybe get better results. But for now, let's say you reach this step, you're satisfied with your segmentation, and the nuclei look clean to you. Now you're ready to segment these cells from each other, which the next step is to separate the touching cells from each other. So if you go to, again, process, binary, and you do watershed, so you can see these small lines between the cells start to form. And the reason I said to get rid of all the holes within the nuclei is important, because sometimes if you look at the nuclei here and you ask yourself why the algorithm designed to segment it this way, although this one cell, it's that because there was some holes within nuclei, within this nuclei. So that's why it's important to have a clean image. Now, after that, we're ready to count the cells. Let's say we're good at this point. We can go to Analyze, and we can select Analyze Particles. And there are different options within this module. You have a control over the size, so the minimum size and the maximum size for the counting process. You have control over the circularity of the object, and you can show the result in different ways. Let's for now go. And if you look at the image, there are like very small, tiny nuclei that might not be real. They're there just because some noise in the image. You can put a minimum size of the counting process. And depending on the resolution and the size of your image, you want to like change this interactively so that you exclude noisy nuclei and just keep all the real nuclei. So let's say put here 20 or 200, let's say, as the minimum size, and the maximum size, there is no limit to it. And then we hit OK. It's going to count all the nuclei for you. You can see the smaller ones didn't get included based on my criteria. We can increase that or decrease that based on the visual inspection between this image and the original image. And as in the results, a tab will show up, our new window will show up, and one of the results will be here 614. The count is 614, which is the count of the objects or the particles within the image. In our case, the count of all the nuclei within the image. Okay, so now you save this number. You might want to save also this image for later use and comparison with maybe a revised version if you want to revise it, stuff like that. So that's the first step to detect nuclei and count them. Now let's move on to the next step, which how we can detect the probe and count the particles there. So let me close out of this. Okay. Just a second. Okay, so now for this, for probe detection, we're going to use another plugin within the Fiji ImageJ. It's called weka classifier. So we're going to go down to the segmentation options. We're going to choose Trainable weka segmentation. This is going to load the image within another window. So which gives you a lot of options to apply classification or solve a classification problem. If you look at the right-hand side, there will be the labels that are available for you. You can see there are two classes at the beginning. For our cases, since we're dealing with 3 colors, we're going to use another class for background. So we're going to use one for probe, one for background, one for nuclei, and one for the background. On the left, you have the option to train classifier, load classifier, and even load data. And also there are settings. For the purpose of this demo, we're going to use the default settings. They work very well. And the classifier name fast random forest. I mean, if you go inside this, you have a lot of classifiers that are available to you. Like, it depends at the end on the speed that you want the results to be in and the accuracy of the results. You can, try different classifiers. For our images, as a compromise between speed and accuracy, fast random forest, the default option gives pretty good results. So we're not going to change the defaults here, but feel free to try other classifiers. Now first, let's add a background label here. So let's say create new class, and I'm going to call the background. So now you have as you can see, we have 3 labels that we have the option to add examples to. Now let's start adding these examples. So let's zoom in. And you have control over this from the main ImageJ module. So let's start with the probe, give a couple of examples for probe. So I'm going to use here the freehand selection tool. I'm going to select different examples. So here's one example, for example. Yeah. And I'm going to click Add to Class. And you can see this reference. This tells me where this area is. If you click it, it will highlight it for you. It's important to choose different examples, like probe on top of background, a probe on top of hematoxin, like here. And let's say we want a lighter one, lighter example, like so. Add to class. So these probe examples. The second class, let's say it's the nuclei. So let's give a couple of examples as well. So we're going to select the region again, then the nuclei, and we're going to hit Add to Class too. And now it's different color, which is the green for this class or for this label. So say this is a lighter example. I will say class 2. Please zoom out actually and go different direction. zoom in here. And let's say, go back to the freehand tool and select this as another example. The last class will be the background. So different examples as well. That's my background. That's my background. Now this, the initial selection, we'll run the classifier. Let's train the classifier. I hit train classifier. And it depends on the size of the images that you are processing and also the number of regions that you have chosen and the classifier itself that you're choosing. It's going to take, usually in a good computer, it's going to take about a minute or two. And the way that you can check it's running in the background, you can monitor the status bar here under ImageJ. You can see that there is updated bars comes up to show you the status of the classification process. Now let's wait another 30 minutes and see the result of this selection. Now to classifying the image after finding the model, and this is what we get. So again, the green will be your nuclei, the red will be your probe, and the background will be in purple color. So now, don't expect this to work from the first time, because at the end it's a classification problem, and you need to give examples of all kinds of cases where that label or that class occur. So the way I usually do it, I initialize my classes with, let's say, 3-4 regions for each class, and then I start toggling back and forth to see if I'm detecting all the probe or I'm over-segmenting or under-segmenting. Now, the next step is to clean up this result. You want to look where the classification failed and give examples appropriately. So let's say here there's over-segmentation. It tells me there is a probe here in this region if you look here, but there is not. So what you're going to do is go to this region, select this over-segmentation, and add it to class 2 as another example. So let's do that for the probe. Let's zoom out, see how it did other regions too. Toggle back and forth. Say here. So you can see there is over-segmentation here for these dark nuclei. So I would add these as examples for the nuclei. Now let's say if I miss something in the probe itself. Zoom in here. The probe segmentation did pretty good, except for the over-segmentation. So after adding the bad examples, like several points or regions that represent these bad segmentations, I can click Train Classifier again. And this should take shorter now. Now you can see after adding these examples, I get much clearer results. Now I have probe signal, and the nuclei signal is much cleaner. Sept now, let me toggle I missed it again. So don't be frustrated by this, because at the end, it's a model you're going to create for the classification here. It's a matter of choosing the correct examples. So we're going to add this now as an example of the probe. So again, let under segmentation happen, add the class, and then train classifier. Again, and should be able to capture this whole region now. Now I think I got pretty good results looking all over this image. And you toggle back and forth to see if you missed or over-segmented anything. And it's just like a matter of adding the bad segmented regions as examples to the classes and retrain your classifier. At this point, you can save your classifier if you want to try it in a different image that has similar color characteristics, or you can reuse it later for comparison purposes between different classifiers. But for now, let's export the results. So we're going to click Create Results, and what comes out is this image. So this image has 3 classes in it. Purple background, green is the nuclei, and red is the probe itself. What we're going to do next is you can either save it at this point, or you can just threshold it right away to get just the probe signal. So we're going to go threshold, and you want to choose here the dark background option, and you want to change these until you get just the probe signal, as you can see here. So different settings or different numbers will give you different classes. So what we want is this one. So we can now hit apply, and this is what we get. Now at this point, what we can do is go again, analyze particles. I think the probe is smaller. Let's report everything. And we can clean it up later when you have export the result as Excel sheet. So let's capture or count everything within this image, regardless of the size. And then you hit OK. It should count everything for you, and now you have the results. The results window comes out, and it's basically give you information about each particle, and what we are interested in is the area in the image. And for this particular classification, it captures about 2,000 particles within this image. However, like any image processing algorithm and any imaging condition, I should say, there should be noise in the image and there will be misclassified pixels. Typically, like to clean these out, what you're going to do is first you want to visually compare the 2 images to see like if your classification works or not, and optimize it thereafter. But also there are tiny particles that don't represent the real dot, single dot for the probe. So the best way to do that is you want to go back to your original image, and estimate what a single dot, number of pixels within the single dot should be, and then based on that number, you're going to get rid of very small results. Like here, let me show the table again. Let me actually do this. Let me do it again. Okay, my last table for all these. There we go. The results. So there are tiny pixels or tiny particles, and we can get rid of these by estimating what a real small dot or single dot size will be by just eyeballing the original image and visually estimate that particle. But let me first, what you want to do at this point is save your results as an Excel sheet or a CSV file. Let's save it here. Step 2. And let's open the image again, just to show you what I'm doing. You close all this. So that's my image. You want to zoom in and find single dots and estimate how many pixels. Then let's say this is one dot. You can see there is like almost 3 by 3 pixels for this dot. And just tell you there's 9 pixels for the dot. You're going to take this number and process your Excel sheet to reflect this. So let me open the Excel sheet. So we're going to do this. We're going to divide the area by 9 to find how many dots within each. And we're going to round this number. And you're going to process all your particles based on that. So let's reflect this formula to all particles. So, and this number will be the number of dots for each particle. And then you're going to take the sum to find the number of dots in the whole image. In this case, I have F2 to F1, T. So that tells you how many single copies within the image. And then you're going to take that number and divide it by the number of nuclei that we found in the first step. So I think it was 600 something. So it's going to be this number divided by, I think, 614 or something like that. And this will be the average copies per cell that you found. Now, please note, like, for this demo, I didn't eyeball like accuracy for classification, but in a normal situation, what you want to do is keep optimizing your classifier until you think you detected all, until you really, like, almost sure you detected most of the dots, and you're not over-segmenting or under-segmenting any of these classes. And that will be it to report the average dots per cell for an entire image using ImageJ and using the singlplex chromogenic assay. So always with questions, please feel free to contact us at any time. You can contact us by email, by phone, or go to our website where we have a techno describing all the steps for this demo. You can download